Hello guys, this is Dr. Maharzan. I hope you guys are doing great. Uh, so today I'm just gonna review some of the problems which I'm pretty sure you guys have already done during our regular class session, and this might help you in your exam 2 preparation. So I just randomly picked these problems from activity manual and my sample example problems, so this will help you in exam prep. So I will get started with work energy and energy conservation, because that's going to be our first topic for the exam 2. So when you do work energy and energy conservation, the very basic and the most important theorem is called work energy theorem. And it simply says the net work done on any object is equal to change in kinetic energy, as you know. And the work done, however, may be different type. So it could be the work done by constant force. If the force is constant, then it's just the dot product between force and the displacement, which is Fs cos theta, where theta is the smaller angle between force and displacement. If, however, if the force is variable, then you will have to integrate that force function and then find the net force. And in some few cases, you will be given the area and you will be given the graph, and you will have to find the net area under the curve, which will represent the net force. So I'm gonna show you at least one problem from each category, and we'll use the net work done to solve some work energy theorem. Okay, I'm gonna just pick some random problems, like I said. So the first problem is, this is work done by a constant force. Here this block, 20 kilogram block, is being pulled by a force across a level floor. It has some friction. Actually, the frictional coefficient is given over a distance. This is the displacement, and you apply a constant force of 60 newtons at angle 30 degrees as shown in the figure. So the first part of the question is, what's the what's the work done by each individual forces here? Because this is the tension force, pulling force, there are normal force, there are frictional force, force of gravity. So it's just acting for work done by, first part is the work done by all these forces. So I'm just gonna do the free body diagram first. So here's the block, here's the pulling force given, here's the gravity, and this is the frictional force because there's some friction, and what else, and then the normal force, and this is making some angle 30 degree. So I'm just gonna quickly calculate work done by all these forces. So first of all, the work done by this pulling force is just Fs cos theta, and it's 60, so 4 meters, and cos of 30 degree. So work done by this force is, you can see, you can calculate that, and that's going to be 200, positive 208 joules. So now interesting part is work done by normal force. So you make sure you know what's the angle between the force and displacement in each case. So in this case, as you can see, the work done, the normal force makes a 90 degree angle, cos of 90 degree. And you don't need to know all these. I'm sorry, this is force of normal force. It's just 0 because cos 90 is 0. So similarly, work done by the gravity is also 0 because here it makes 90 degree angle. And work done by frictional force oops, is, as you can see, frictional force displacement cos of 180 degree, because as you can see here it makes 180 degree. But however, force of friction is mu k times n, and normal force, so first you have to solve for the normal force here. So I'm just gonna apply Newton's second law in y direction, which is mass times this. You have n plus f cos theta, right, minus mg is mass times acceleration, but there's no acceleration in y direction. So you can solve for normal force first. So if you do that, the normal force will be 166 Newton if you put all these numbers. And then you can find the frictional force, which is mu k times n. So mu k is given to us 0.2, and the frictional force is going to be 33.2 newtons, and then you put it here and solve for the cos 180 degree is -1. So work done by frictional force is negative 130 joules. As you can see, right, the work done by the frictional force is negative, which is what we expect. Now so for part B, it says what is the speed at the end of the 4 meters after 4 meters. So it's just asking the final velocity. Its initial velocity of the block is given. It was moving at 2 meters per second. So then we can use the work energy theorem. So it simply says the net work done on the block is change in kinetic energy, right, which is 1/2 mass velocity square minus 1/2 mass initial square. But net work done is the sum of all these works, right? So work done by pulling force, work done by normal force, plus work done by gravity, plus work done by the frictional force, and that will all give you positive 75 joules is equal to 1/2 mass. So we're calculating the final velocity minus 1/2 mass. Initial velocity is 2 meters per second. So if you solve that, so final velocity is going to be 3.4 meters per second. That's what you get. And you can see the initial velocity was 2 meters per second, and it speeds up, and that's what we expect because there was a positive work done. The net work done on this object is positive. That's why it increases the velocity. Okay, that's how you solve the work done by constant force, and use that to find the net force first, and use the work energy theorem. Okay, so I'm gonna now go to the second type of problem. So here, if say force and displacements are given in unit vector notation, right? So how would you solve the work done by each force, work done by this force? So for example, you're given this force in ijk notation, unit vector notation, which is a constant force, but it has two components. Similar, the displacement has also two components. So first question is, what's the net work done by this force? So remember, the work done is just the dot product, right? And which is if you remember from dot product between two vectors, it will get you a scalar quantity, which is a work done. And that's gonna give you all the products of each components, right? So I'm just gonna multiply all these each components together like that. Y component is 3, -2, and there's no Z component for both. So that's gonna get you positive 14 joules, right? So that's the first question. It's just a dot product. This is called dot product between two vectors. So it will give you a scalar number. If you take the dot product between two vectors, the result will be a scalar quantity. So second question was the angle between two vectors. So then we know that f dot d, which we already know, is also equal to fd cos theta, right? Which we already found 14 joules. So then you can solve for the f and d. And remember, this is the magnitudes, this f and d here. So first you'll have to solve for the magnitudes, which is this, right? From, because each, you know that each component, it's 3, 4, 5 newtons, and the magnitude of the displacement is also this. This is going to give you the displacement as 5.4 meters, and then after that you just plug it back here. 14 divided by 5 times 5.4, so this is cos theta. So theta will be inverse cos of this quantity, and that's going to give you about 59 degrees. So that's the angle between force and displacement. So that's how you calculate. Okay. All right. So I will just continue. So picking some random problems. So here's the next question. The potential energy function is given by this equation, right? It's something is some spring force, non-ideal spring force, you know. Find the force function, and here's the hints. Hints is given to you, and this is pretty easy one because we know the formula. You know, the force is just the negative gradient, potential gradient. This is called potential gradient. So force is just a negative potential gradient, right? So just need to take the derivative of this potential energy function. And potential energy gradient actually. So, but don't forget the negative sign. So then, so we are taking the derivative, right, with respect to x. So that's why it's going to give you 1/2 mg negative negative plus 1/2 2kx. So that's going to give you plus kx. So that's your force function. That's it. So remember this formula. So force is just the negative potential energy gradient. Okay. All right. So now using the same concept, this, you know, so I'll show you the next problem. So which is this. So this is a potential energy. U is potential energy, you know, as a function of x, and it has a curve. So potential energy changes as a function of x like this, and you're assigned various functions at various points 1 2 3 4 5, and it's asking at what point will the force have the largest magnitude. Remember, just a reminder, force is negative potential gradient, right? So if you just want to find the magnitude, is just the slope, right? Just the slope of u versus x curve. So you just need to calculate the slope. So since it's asking the largest magnitude, so it has a largest magnitude at, I guess, 0.1, because as you can eyeball, right, it has the largest magnitude. So what is the direction of the force at point chosen at A? So direction of the force here, since it has a positive slope, right, so the direction should be negative, right, because this is negative du over dx. So since the slope is positive, so the force must have a negative direction. Are there any points where the force is 0? Yes. So here at point 4 and point 2, the slope is 0. 2 and 4, the force is 0 because slope is 0. Alright guys, so that's how you solve potential energy function, short question. Okay, let's move on. So I'm going to show you a very quick question. An object moves in a circular path. The work done by the radial force, radial force is 0, y, right? So for example, an object is moving in a circular path, and let's say this object is moving counterclockwise like this, and the radial force is towards the center like this, and it says why the work done by this radial force is 0, and the answer is this: because the force at any moment, the angle between force and this displacement is 90 degrees. So that makes the work done by radial force 0, because it makes F s cos of 90 degree. Okay, just a quick one. Okay, next. So this is the last example of work done. It's a graphical one. So if you are given force versus x, right, this is a force in Newton in y axis, and x axis is given in distance in millimeters. So you should be able to find the work done, from this graph. And remember, net work done is this, and this is nothing. This is just the area under force versus x curve, right? Because this is the integral of the force function, so that has to do with area under the curve. So it says, first question is, what's the net work done from 0 to 80 millimeter? So 0 to 80 millimeter is symmetrical, right? So work done, positive work done and negative work done will cancel out, 0, because this is symmetrical. So next is from 0 to 60 millimeter. So 0 to 60 millimeter, right? So then you'll have to do the work done first part. The net work done is work done positive part, right? And the negative part is negative work, because this work is negative. So work done 1 is 1/2 20 newtons times base, which is 40 millimeter, right? So that's the positive work, and negative work is again 1/2, because area of a triangle is 1/2 height times base. So 1/2 is 20 millimeter, right? times height is 10. So that's going to give you the net work done, and that should give you 0.3 joules. All right, so that's how you solve, work done, by a graphical method. Okay, so the next one is, so let me solve one short question on power. So power, first of all, power is rate of doing work, delta W over delta T. So this gives you the average power, and instantaneous power is dW over dt, rate of doing work. Right, so it says, and sometimes it may ask you in terms of different variables. So work done is F dx. So if force is constant, so work done, so power produced by a constant force is also given by this. Its unit is joules per second, watts. Okay, back to this question. So a 5 kilogram block is acted by a net force in x direction, does 500 joules of work, distance 10 meters in 4 seconds. So calculate the rate of doing work. So the average power produced by this object is just the rate of doing it. So 500 joules is done in 4 seconds. So 125 watts. Okay. Okay, next one is, now here's the question. You have a ball of mass 100 gram is attached to the string. First it is kept horizontal, and then you release from this initial point. This is the initial point. You release this object, and it's acting. What is the tension in the string when the ball is at the lowest point? When the ball gets here at the lowest point, what is the tension? So when you have problems like this, you will have to combine two concepts. So you'll have to combine Newton's second law and energy conservation. So let's try to solve that. First of all, first I'm going to apply Newton's second law at the lowest point. When the object gets to the lowest point, what's the free body diagram? So first I'm going to draw the free body diagram. So you have tension force, because it's going in a circular path like that. So you have a tension force, you have mass times gravity, but since it's moving in a circular path, it must have an radial acceleration in that direction. So if you apply Newton's second law, let's say in y direction, so you have this T minus mg is m, and this is v square over r. So r is length of the string. So T is mg plus mv square over L. But the problem is we don't know the speed when the ball go through the lowest point. We don't know the speed, but we can find out, calculate the speed v at the lowest point using energy conservation. And energy conservation said U plus K top, U plus K bottom, right? So before you release the ball, all energy is potential energy. So the total height is L. So mgl plus, there's no kinetic energy initially. So when it gets to the bottom, lowest point, there's no potential energy because this is our reference point, 0. So all energy is kinetic energy. So you can cancel out mass. So V will square will be 2gl. Right, mass will cancel out, 2gl. So, and then you can plug this V square back to equation number 1 and solve for tension. So then tension is going to be mass times gravity plus m over L, but V square is 2gl. So L will cancel out, is 3 mg. Okay, tension in this string, in this case, is 3 times mass times gravity. Okay, all right. So I'm going to solve a couple more problems on energy. So for example, so if you have, again, this is work done by, work done by variable force, as you can see. And these are all similar problems. So I will solve some of this problem. Okay, so let me solve number 3. So number 3 says a block of mass to 2 kilogram compresses spring by 11 meter and is then released from a rest horizontal level surface. After being released from the spring, it passes through rock paths and then continues to travel on this until it reaches. Okay, so it has many concepts, it has many parts, so let me try to draw the picture. Okay, so you have a level floor, a mass is released with by compressing a spring, and its spring constant is given, and you compress it by 11 meters, right? And then you release it by compressing this, and it go through and it, after being released from the spring, it passes through a rock patch. So once you release it, it goes through some rock patch. Once you release it, so let's say it has some initial velocity right after releasing, right? And it goes through some, so let's say the rock patch has a length L, right? And after that it has mu k, and then after that, after passing this rock patch of length L, it continues travel along a smooth level, no friction here, until a frictionless hill. So it then encounters a frictionless hill like this, and then finally rises a maximum height of this total height 0.920. No, I'm sorry. So it says it rises up to, so finally after rising that much height, it comes to rest. That's what it says. So finally it comes to rest after climbing that much, 0.9 meter. So based on this information, first question is, what's the length of the rough patch? All right, and that's it. And then, so for this problem, we can completely use the energy conservation, right, in the presence of non-conservative force. And this is like this, U plus K initial, but since there's some rough patch, it will lose some energy. And if you see, the formula is the work done by non-conservative force, which is the frictional force, and finally U plus K final. right? So initially all this energy is stored as spring energy, spring elastic energy. There's no kinetic energy, right? And this is mu k, n times L is the work done by frictional force. So finally, when it climbs uphill and finally comes to rest, so all energy is potential energy. So that should be your equation, and you're solving L. So then 1/2 kx square minus mgh is mu k normal force here. This is on a level floor, so mass times gravity is the normal force, L. So L is 1/2 kx square minus mgh divided by mu k mg. So this is your L, the length of this rough patch, and you can put all these numbers. You can put all the numbers, because all these variables are given, and then find the length of this rough patch. So that's the first question. Second question it is asking is, what's the work done by the frictional force? And now, since we already know this length of the rough patch, so work done by frictional force is simply mu k times n times L, right? And that's mu k mg L, and L is given by that. Alright, so now I'm gonna solve the next question, which is this. And again, this is a combined question. So it says an object of mass m makes a loop the loop as shown in the diagram. When it is upside down at the point A, which is the top of the loop, the normal force is found to be twice mg, 2 times mass times gravity. What is the speed of the object at point A in terms of g and r? And what is the normal force at B, neglecting any friction or air resistance? So how would you solve that? So first of all, it says when the first question. So let me redraw that. When this mass reaches the top of the loop, it says the normal force. This is the free body diagram when it reaches the top of the loop, right? Mass times gravity, and what else? So you have radial acceleration that way. But normal force is given to us. It says too. So if you solve the Newton's second law at the top of the loop, is this. So sum of the forces N plus mg together provides the centripetal radial force, which is this, right? But this is twice mg plus mg is mv square over r. So this is 3 mass times gravity is mv square over r, and we're supposed to solve the speed in terms of g and r. So speed will be 3gr squared. So that should be your answer. So speed of this block when it reaches the top of the loop should be square root of 3gr, right? But it should give you the normal force. It's given in terms of this. So second part is, what is the normal force at point B? So again, when it reaches the bottom loop, this is the free body diagram. So you have mass times gravity, you have normal force, but since it's going in a loop, its acceleration has to be towards the center. So your free body diagram is this, and Newton's second law must be N minus mg is mv square over r, and you're solving the normal force and assuming that the speed is constant. Speed here is a uniform circular motion, so we assume that the speed is this is moving with constant speed. And it's acting, the normal force is mg plus mv square over r, and you can now complete that. Plus m over v square is 3gr, right? So it's 3 mg 4 mg. So normal force, right, when it reaches the bottom of the loop is 4 mg, and the normal force when it is at point A is twice mg. So you can clearly see the normal force at B is greater than normal force at A. And if it is a roller coaster, we have done so many problems based on that. If it is a roller coaster, normal force is your apparent weight, the weight you feel. So you feel heavier when you reach the bottom of the roller coaster. So something like that. So I'll be solving more problems. This is the first part, just the simple work and energy, and then I'll be solving more problems, which will be the second part of the review problems.